Hi, in this video we're going to talk about how do we check continuity and describe end behavior of functions. First of all, what the heck is continuity? That's talking about, is a function continuous? Well, what is that? A continuous function has no breaks, no holes, or gaps, okay? Basically you can trace the function without lifting your pencil. But what if you can't trace the function without lifting your pencil? Well, then you'll run into one of these three types of discontinuity: infinite discontinuity, jump, or removable discontinuity. Infinite discontinuity is whenever you have some asymptote that is interrupting your function, right? And these tails just go off to negative and positive infinity. Jump discontinuity typically happens with piecewise functions where they're approaching the same x value, but from the left and right they're not hit on the same y value. And finally, removable discontinuity is just whenever you have a hole in your function. All right, the continuity test. To see if a function is continuous at a certain point, we got to do a few things. First, simplify the function to identify holes. If something in the numerator cancels something in the denominator, we have a hole. Then we'll verify that the point exists that they want us to check. Then we'll use a table, typically in our calculator, to see if the function approaches the same y value at that point from left and right. The reason to check this last part about the left and right is because, see here, f of 2 exists. F of 2 exists right here, but it doesn't approach from the left and right, so we wouldn't be able to trace this with a pencil without lifting the pencil. So let's try that. Let's see for if f of x equals x plus 3 over x squared minus 9, is it continuous at x equals 3 and negative 3? Well, the first step was to simplify the equation to check for any holes. And after factoring the denominator, we see that we get a hole at x equals negative 3. Okay, so now we're dealing with f of x is equal to 1 over x minus 3. So we've already taken care of the x equals negative 3. Let's verify if x equals 3 exists. F of 3 would be 1 over 3 minus 3, which is 1 over 0. So this also does not exist. So now we have to figure out what type of discontinuity it is. It's not removable because we already found all the removable. To do this, use your calculator to build a table where you get numbers that are approaching 3 from the left and from the right. Filling in this table, you can see that as it approaches 3 from the left, it gets more and more negative, so it's going off to negative infinity. Whereas it approaches 3 from the right, it's going off to positive infinity. So here we have an asymptote. So here we have infinite discontinuity at x equals 3. For the sake of the notes, here's a graph. You see, just like as the table suggests, here's x equals 3. As the graph approaches 3 from the left, it goes off to negative infinity, and from the right, it goes off to positive infinity. The next section of the notes is end behavior, which just describes how a function behaves at the end of the graph. And to describe end behavior, we'll use limit notation, something that we'll explain later in the year as we get closer and closer to calculus. But here's what it looks like. Before we jump into the actual end behavior of this blue line here, or this function here, we have to understand these parts. See, these arrows mean goes to. So as x goes to negative infinity, right? So as we go off to the left or going off to the right, that's x going to positive infinity. If the function goes up, that's our range, right? F of x. That's f of x going to positive infinity, or down f of x going to negative infinity. So now let's actually look at this blue curve. All right, and so here's the notation. The limit as x goes to negative infinity of f of x. Well, all that means that as x goes left, which way does y go, up or down? Well, as the x values go left, these y values are going up to positive infinity. So over here with the limit as x goes to infinity, so as x goes right, which way do the y values go? They go down to negative infinity. All right, you try. Try describing the end behavior of this function using this limit notation. Go ahead and pause the video. All right, hopefully you got positive infinity for both sides, because as x goes left, y goes up. As x goes right, y also goes up. Another way you can tell in behavior just by looking at a function is by looking at the degree of the polynomial and the leading coefficient. I'm not going to write this in the limit notation like it has been, but you can get the picture. If the degree of the polynomial is even, then the tails like to end the same. So if they're positive, the tails will both end up. And if the leading coefficient is negative, they'll both end going down. If they're odd, they like to end in opposite directions. If it's positive, it'll end to the right going up, so it'll start down. And if it's negative, it'll start by going positive and then end going off to negative infinity. So this is like a nice little table to have as well. Let's do one quick example of that. Here we have f of x equals negative 2x to the fifth plus 3x squared minus 7. Well, the degree of the polynomial is 5, and the leading coefficient is negative 2. So we have an odd degree with a negative. So I know that my tail should look something like this. So in my limit notation, as x goes to the left, the function goes off to positive infinity. And as the function goes to the right, the function goes to negative infinity. And there, we did it without even needing a graph. All right, that's everything for continuity and in behavior. Goodbye.